Hello, friend. Welcome back to another quiet journey through the cosmos. Tonight, we're going to talk about something extraordinary, something ancient, something still happening even now as you listen. Some nights when you look up at the darkness between stars, you might wonder what you're really seeing. Most people think they're looking at empty space, black nothing, the absence of light. But that's not quite true. Because right now, at this very moment, the oldest light in the universe is falling softly onto your skin. Light that began its journey before the first stars were born. Before galaxies learned to spiral. Before anything you could point to and call a thing even existed. This light has been traveling for nearly 14 billion years. And tonight it's still reaching us. The universe, it seems, has a long memory. And light is how it remembers. Before we drift into this story together, I want to say thank you for being here. These quiet moments we share mean more than you might know. If you find comfort in these late-night journeys through science and wonder, you might like to stay a while. You can gently tap the like button, subscribe, if you'd like more stories told softly, and ring the little bell not for noise, but so the next quiet night can find you again. There's no pressure, just an invitation to wander together. Now, let's drift. Tonight we're going to explore the oldest light in the universe. Scientists call it the cosmic microwave background, or CMB for short. But that name doesn't quite capture what it really is. It's not just radiation. It's not just data on a graph. It's the afterglow of creation itself, the very first light that was ever free to travel through space. And somehow, impossibly, it's still traveling, still reaching us. Still whispering stories about a time when the universe was young and wild and nothing like it is now. You don't need to understand everything. Just rest and let curiosity do the listening. Imagine, if you can, a photograph, not of a person or a place, but of the entire universe when it was just 380,000 years old. A baby universe, smaller than it is now, but already unimaginably vast, hot, dense, glowing. That photograph exists, not on paper, of course, but encoded in light. Light that has been traveling toward us ever since that moment, crossing distances so enormous that numbers stop meaning much. And when scientists finally learned how to see this light, how to read it, they found something stunning. They found the universe's first portrait, a snapshot of everything taken at the very beginning. But here's what makes it strange. Here's what makes it beautiful. This isn't just history. It's not locked away in some cosmic archive. It's happening now. The light from that infant universe is still pouring into our world. It passes through walls, through your body, through the air between these words and your thoughts. Every single second, billions of these ancient photons arrive at Earth, carrying memories of a time before time had much meaning. You can't see them with your eyes. They have been stretched too thin by the expansion of space, pulled into wavelengths that our retinas can't detect. But they're here, constant, patient, endless. And if you had the right kind of radio tuned to the right frequency, you could hear them. A soft, steady hiss, static from the edge of everything. The universe still humming the first note it ever sang. Let me tell you what this light looked like when it was born. Imagine the whole universe filled with something like fog. Not water vapor, but a thick soup of particles. Protons, electrons, photons of light trying to move, trying to travel, but getting scattered and bounced and trapped by all those charged particles swirling around them. The universe was opaque then. Light couldn't go anywhere. It was born into a cage it couldn't see. Everywhere it tried to go, it ran into something. An electron here, a proton there, endless collisions, endless imprisonment. For 380,000 years, light had no freedom. It could not journey. It could not escape. But the universe was cooling, expanding, thinning out. And as it cooled, something remarkable happened. The temperature dropped just enough down to about 3,000 degrees. Kelvin, roughly the surface temperature of a red dwarf star, for electrons and protons to do something they'd never done before. They joined together, They became hydrogen atoms, neutral, stable. And suddenly, the fog lifted. The universe became transparent. For the first time, light could move without being scattered. It was set free. Scientists call this moment recombination. Though that's a slightly misleading name, since nothing was actually recombining, it was the first combination. But names aside, this was the moment. The moment light stopped being trapped and started being travelers. Photons that had been pinballed around for hundreds of thousands of years suddenly had open space ahead of them, and they went in every direction, outward, endlessly outward. That light is what we call the cosmic microwave background. Now, you might be wondering something. You might be thinking, if this light was released 13.8 billion years ago, shouldn't it be long gone by now? Shouldn't it have raced past us out into the farther reaches of space, never to return? That's a reasonable thought. Light moves fast. The fastest thing there is. 299,792,458 meters every single second. At that speed, you'd think it would have left us behind long ago. But here's the thing. Here's the beautiful, strange thing. The universe has been expanding the whole time, not just growing, but stretching. The space between things is getting larger. And when space stretches, it stretches everything in it, including light. So those photons that left the infant universe racing outward in all directions, they're still racing. They've been racing for nearly 14 billion years. But the space they're racing through has been growing beneath them like a runner on a treadmill that keeps speeding up. Some of that the light that happened to be traveling in our direction is only just now arriving, not because it was slow, but because the journey was so incomprehensibly long and keeps getting longer. Think of it this way. When that light began its journey, there was no Earth, no sun, no Milky Way galaxy. The atoms that would one day become your body were scattered across the universe, not even close to meeting each other yet. And that light, those photons, have been traveling the entire time. Through the birth of the first stars, through the formation of galaxies, through supernovae and collisions and cosmic dark ages. They've been moving uninterrupted for longer than almost anything else in existence. And now tonight, they're here, falling onto this planet, onto you. There's something almost tender about that, something patient. When scientists first started searching for this light, they didn't quite know what they'd find. They had predictions, of course, theories, mathematics that suggested the afterglow of the Big Bang should still be detectable, cooled down by billions of years of expansion into a faint whisper of microwave radiation. But predictions and proof are different things. And in 1964, two scientists named Arno Penzias and Robert Wilson stumbled onto something strange while working with a radio antenna in New Jersey. They kept picking up noise, a persistent hiss that wouldn't go away no matter what they tried. They checked for interference, cleaned pigeon droppings out of the antenna, pointed it in different directions. Nothing worked. The noise was everywhere, uniform, constant. It took them a while to realize what they'd found, but when they did, when other scientists helped them understand what that hiss actually was, it changed everything. They detected the cosmic microwave background, the relic radiation from the infant universe, the echo of creation. And for that discovery, they won the Nobel Prize in Physics in 1978. But that was just the beginning. Because once scientists knew the CMB was real, they wanted to see it more clearly, to map it, to understand what it could tell them. And over the following decades, they launched satellites designed to do exactly that. First came COBE, the Cosmic Background Explorer, in 1989. Then WMAP, the Wilkinson Microwave Anisotropy Probe, in 2001. And finally, Planck launched in 2009, which gave us the most detailed map of the early universe we've ever had. Each mission peeled back another layer of mystery. Each one revealed the universe's first light in finer and finer detail, and what they saw was breathtaking. Not perfectly smooth light as you might expect, but light with tiny ripples in it. Temperature variations of only a few millionths of a degree. Hot spots and cool spots scattered across the sky like freckles on skin. These weren't flaws, they were seeds. The very beginnings of structure. The places where billions of years later, galaxies would form. Where stars would ignite. Where planets would coalesce. In that ancient light, we can see the fingerprints of everything that came after. But here's what really gets me. Here's the part that feels almost like poetry. This light has traveled so far for so long that it's changed. When it was first released, it was visible light, warm, orange and red glowing like embers. But as the universe expanded the space, it was traveling through stretched. And when space stretches, light stretches too. Its wavelength gets longer, its energy gets lower, so that visible light over billions of years has been pulled and pulled and pulled until it's no longer something your eyes can see. It's been redshifted into microwaves, invisible, silent, but still there, still carrying the same information it always did. Just in a different language now. The universe speaks quietly these days, but it still speaks. You know, there's something humbling about this. Every night, whether you think about it or not, the oldest light in existence is passing through you, through your home, through the air and the walls and the sky. It doesn't ask for attention, it doesn't announce itself. It just arrives constant and patient, the way old things often are. And it's been doing this since long before humans existed, before dinosaurs, before the first single-celled organisms figured out how to divide. This light was already on its way, and it will keep coming, long after we're gone, long after our sun burns out, and the Earth is nothing but a cold memory. That light will still be traveling, still reaching whatever comes next. There's a kind of comfort in that, I think. A reminder that we're part of something much larger and much older than we usually remember. That the story didn't start with us, and it won't end with us either. But tonight, right now, we get to listen to it. We get to hear what the universe was like when it was young, when it was simple, when it was just light finally learning how to fly. So as we move forward through this story, as we drift deeper into the science and the history and the mysteries of this ancient glow, I want you to hold on to that feeling. The feeling that you're connected to something impossibly vast. That the light touching you now began its journey before almost anything else existed. And that in some small, quiet way, you're part of this. Part of the universe remembering itself. Now, if you're ready, let's go back even further. Back to a time when light couldn't escape at all. When the universe was so hot and so dense that even photons were prisoners. We'll explore what it was like before this moment of freedom. Before the light was set free. Because to understand why this ancient glow is still reaching us, we need to understand where it came from. And what it had to survive to get here. There was a time when light had nowhere to go, when every photon born into the universe was immediately caught, scattered, trapped in an endless maze of collisions. This wasn't darkness exactly. It was something stranger. The universe was glowing, blazing hot, but that light couldn't travel, couldn't escape, couldn't become the thing we think of when we picture light, something that moves freely through space, carrying information from one place to another. For hundreds of thousands of years, light was a prisoner, and tonight we're going back to that time, to understand what the universe was like before the oldest light could begin its journey to us. Imagine being born with eyes that couldn't see farther than your own hand. Not because of blindness, but because the air itself was too thick, too full of stuff. That's what the early universe was like for light. Opaque, impenetrable. A fog so dense that nothing could pass through it. Scientists call this period the Dark Ages of the universe, though that name is a little misleading. It wasn't dark at all. It was incredibly bright, glowing white hot, but the light couldn't go anywhere. And without light that travels without photons that can carry images and information across distances, there's no way to see, no way to know. So, in a sense, even though the universe was full of light, it was also invisible to itself. Let's step into that world for a moment. Let's go back to a time just after the Big Bang. We're talking about the first few minutes here, maybe the first hour. The universe is unimaginably small compared to what it will become, but it's already expanding, cooling, changing, and it's hot. Not campfire hot, not surface of the sun hot. We're talking about temperatures in the trillions of degrees. At that temperature, matter as we know it can't exist. There are no atoms, no molecules, just a seething soup of fundamental particles. Quarks and gluons smashing into each other, combining and breaking apart in fractions of a second. It's chaos, beautiful, energetic chaos. But as the universe expands, it cools. And as it cools, things start to settle down. Quarks bind together to form protons and neutrons, the building blocks of atomic nuclei. Within the first 3 minutes, some of those protons and neutrons start sticking together, forming the very first atomic nuclei. Mostly hydrogen, some helium, tiny traces of lithium. This process is called Big Bang nucleosynthesis, and it's remarkable when you think about it. In just 3 minutes, the universe created the raw materials for everything that would come later. Every star, every planet, every atom in your body started as hydrogen or helium formed in those first few moments. But here's the thing. Even though you now have atomic nuclei floating around you, don't have atoms yet. Because atoms need electrons. And electrons at this point are still flying around freely. They're not bound to anything. The universe is still too hot for that. Anytime an electron gets close to a proton, anytime it tries to settle into orbit and form a neutral hydrogen atom, a high-energy photon comes along and smacks it away, ionizes it, keeps it free. So, what you have is a plasma, a state of matter where electrons and nuclei exist separately swirling around each other, but never quite coming together. And this plasma has a very important property. It's opaque to light. Photons can't travel through it. Every time a photon tries to move, it runs into a free electron and gets scattered, bounced in a random direction. And then it tries again and hits another electron and gets scattered again. Over and over, endlessly. Think of it like this. Imagine you're trying to walk through a crowded room. But the room is so packed with people that you can't take more than a single step before bumping into someone. And every time you bump into someone, you get spun around and sent off in a random direction. You'd never get anywhere, would you? You'd just stumble in place, colliding and bouncing and going nowhere. That's what it was like for light in the early universe, born into a crowd too thick to navigate. This state of affairs lasted for a long time, well, long in cosmic terms. 380,000 years. That might not sound like much compared to the 14 billion years that have passed since then, but when you're talking about the universe's infancy, it's a significant chunk of time. And during all those years, light was trapped. The universe was filled with this glowing, churning plasma, but no light could travel freely. No images could form. No information could cross distances. Scientists sometimes describe this as the universe being foggy. And that's a good metaphor. If you've ever been in really thick fog, you know what it's like. Everything glows softly, but you can't see far. Light scatters off the water droplets in the air, bouncing in every direction, never making it to your eyes in a straight line. The early universe was like that, except instead of water droplets, it was free electrons doing the scattering. And instead of a few meters of visibility, there was essentially zero visibility. Light couldn't travel at all. Now you might wonder why this matters. Why should we care about a time when light was trapped? Well, because it's precisely this trapping, this imprisonment, that makes the cosmic microwave background so special. When light finally did get released, when the fog finally lifted, that first free light became a snapshot. A photograph of the exact moment the universe became transparent. Everything before that moment is hidden from us. Not because it didn't happen, but because there's no light that can carry information from those earlier times. The universe was opaque. It kept its secrets locked away. The CMB is the farthest back we can see, the oldest light we can detect. It's the universe's first visible moment. So what changed? What made the fog lift? The answer is temperature. As the universe continued to expand, it continued to cool. And somewhere around 380,000 years after the Big Bang, the temperature dropped below a critical threshold. It fell to about 3,000 degrees Kelvin. That's still incredibly hot by our standards, hot enough to vaporize any material we know. But it's cool enough for something important to happen. Cool enough for electrons to finally stick to protons. When an electron and a proton come together, they form a hydrogen atom, the simplest atom. One proton in the nucleus, one electron orbiting around it. And crucially, this hydrogen atom is electrically neutral. It has no net charge. And photons don't interact strongly with the neutral atoms the way they do with free electrons. So, when the universe cooled enough for hydrogen atoms to form, when electrons and protons finally paired up across the entire cosmos, the fog lifted. Suddenly, photons could move without being scattered. They were free. This moment is called recombination. Though, as I mentioned earlier, it's a bit of a misnomer because the electrons and protons weren't recombining. They were combining for the first time. But the name stuck. And this event, this transition from plasma to neutral gas, is one of the most important moments in cosmic history. It's the moment the universe became transparent, the moment light could finally escape. And the light that escaped, the very first light to travel freely through space, is what we now detect as the cosmic microwave background. Here's something beautiful about this. When recombination happened, it didn't happen all at once everywhere. It happened over a period of time, maybe a few tens of thousands of years, as different regions of the universe cooled at slightly different rates. But from our perspective, looking back across billions of years, it looks like a single event. A thin shell of light emitted from every point in space at roughly the same time, all heading outward in every direction. And some of that light, the light that happened to be heading toward where we are now, is just arriving. Tonight. After traveling for 13.8 billion years. That's the light we call the CMB. Not the Big Bang itself, not the initial explosion, but the afterglow, the moment the universe stopped being opaque and started being transparent. The first light that could fly. Now let me tell you about what this plasma was actually like. Because it's easy to think of it as just a soup of particles, random and chaotic. But there was structure there. There were patterns. Sound waves, in fact. Before recombination, before the fog lifted, the universe was filled with acoustic oscillations. Pressure waves moving through the plasma like ripples on a pond. These waves were created by tiny variations in density. Tiny clumps where matter was slightly more concentrated than average, and those clumps would compress heat up and then bounce back, creating waves that propagated through the plasma. These sound waves are important because when recombination happened, when the plasma suddenly turned into neutral gas and the photons were released, those waves got frozen into the light. The hot spots and cool spots we see in the CMB today, those tiny temperature variations I mentioned earlier, they're the imprints of those ancient sound waves. Fossil ripples from a time when the universe was small enough for sound to cross it. Scientists call these patterns baryon acoustic oscillations. And by studying them, by measuring their size and shape and distribution, we can learn incredible things about the early universe. We can figure out how much normal matter there was, how much dark matter, how fast the universe was expanding, all from the echoes of sound waves that rang out nearly 14 billion years ago. It's like listening to a bell that was struck at the dawn of time. The sound is long gone, but the vibrations are still there, encoded in light. You know, there's something almost tragic about this period. All that light born and trapped and scattered, never able to travel, never able to see. For hundreds of thousands of years, the universe was blind to itself. And then, in what must have been a breathtaking transition, the fog cleared. The electrons settled down. The photons were freed. And for the first time, the universe could look at itself, could carry information from one place to another, could begin the long process of becoming visible, And we're the beneficiaries of that moment. We're the ones who get to see that first light stretched and redshifted and ancient, but still here, still carrying the story of how the universe learned to see. There's a question that sometimes gets asked. If the universe was opaque before recombination, does that mean nothing happened? Does that mean the universe was just sitting there waiting? Not at all. Enormous things were happening. Structure was forming. Gravity was pulling matter together into clumps that would one day become galaxies. Dark matter was already there, invisibly shaping the way normal matter flowed. The seeds of everything we see today were being planted. But we can't observe it directly. We can't see it. Because light couldn't escape. It's a little like trying to understand what happens inside a star. We know fusion is occurring in the core. We know photons are being created. But those photons don't just fly straight out. They get scattered and absorbed and re-emitted millions of times before they finally reach the surface. It can take tens of thousands of years for a photon born in the core of the sun to make it to the surface and escape into space. The early universe was like that. Light was being created constantly, but it couldn't get out. It was trapped in the crowd. And then finally the crowd dispersed. The electrons paired up with protons. The opacity vanished, and light could run. So, as we think about this time, this strange era when light existed but couldn't travel, let's hold on to the significance of what came next. Because the moment light was set free wasn't just a physical transition. It was the moment the universe's story became tellable. It was the moment we could start to see, to witness, to understand. Before that, everything is theory and mathematics. But after that, we have light. We have evidence. We have the universe's own testimony about what it was like back then. And that testimony is still arriving, still falling softly onto our telescopes and our instruments, still whispering about a time when everything was young and hot and waiting to become. The light has been freed, and now we need to understand what happened to it next. How did it travel across such unimaginable distances? How did it survive for so long? And why, after all this time, is it only just now reaching us? Those are the questions waiting for us as we continue. The journey of light across the expanding universe, patient, relentless, and impossibly long. There are moments in history that change everything. Moments when something locked away suddenly breaks free. When a door that's been closed for ages finally swings open. In the history of the universe, there was one such moment. A transition so profound that it divided all of time into before and after. Before this moment, light was imprisoned. After it, light could fly. And that single instant, the cosmic exhale, is the reason we can see the oldest light in the universe at all. Picture this. The entire cosmos filled with glowing plasma suddenly going quiet. Not dark, not cold, but transparent, clear. As if a thick fog that had covered everything for hundreds of thousands of years lifted all at once, and for the first time, space became space. Empty, crossable, free. 380,000 years after the Big Bang, the universe reached a temperature of about 3,000 degrees Kelvin. And at that precise temperature, something remarkable happened. Electrons stopped running. They settled down. They found their homes orbiting protons, and together they became atoms, neutral hydrogen atoms, simple, stable, and visible to light. And in that moment of combination, the universe transformed. The fog vanished. The opacity disappeared. Light, for the first time since the beginning, could travel without being scattered. It was set free. Scientists call this event photon decoupling. The moment when photons decoupled from matter, when they stopped interacting so violently with electrons and started moving freely through space. And the light that was released in that instant, the very first free light, is what we now call the cosmic microwave background. It's not just any light, it's liberation light, freedom light, the universe's first breath of transparency. Let me paint a picture of what this moment would have looked like if you could somehow witness it. Imagine standing in the early universe surrounded by glowing gas. Everything around you is bright, but you can't see through it. It's like being inside a cloud that's lit from within. You're immersed in light, but there's no distance, no depth, just glow. And then gradually the glow starts to change. The temperature drops. Electrons begin pairing with protons. One by one, atoms form. And as they do, the opacity fades, the fog thins. And suddenly, for the first time, you can see far. You can see across space. The universe opens up before you, like a curtain pulling back. And in that moment, every photon that had been trapped, bouncing uselessly from electron to electron, was suddenly free to go. And they went. In every direction. Outward, endlessly outward, carrying with them a snapshot of what the universe looked like at that exact instant. A photograph taken in light, encoded not on film, but in the wavelengths and temperatures of photons themselves. This moment is sometimes called the surface of last scattering. It's a strange name, but it makes sense when you think about it. Imagine light scattering off electrons like a ball bouncing off walls. For hundreds of thousands of years, that's all light did. Scatter, scatter, scatter. But then, at this moment, the scattering stopped. The photons had their last collision, their last bounce, and after that they flew free. So the surface of last scattering is the boundary between the opaque universe and the transparent one, the edge of the fog, the final wall before open space. And here's what's beautiful. That surface exists everywhere. It's not a place you can point to. It's a moment in time spread across all of space. Every point in the universe went through this transition at roughly the same cosmic age. So when we look out into space, when we look far enough back in time, we see that surface. We see the glow of the last scattering. We see the light that escaped the moment the universe became clear. Now let's talk about what this light actually was when it was born, because this is important. When photon decoupling happened, when the light was freed, it wasn't microwave radiation yet. It was visible light. The universe at 3,000 degrees Kelvin glows in the optical range. Deep red, orange, like the embers of a dying fire or the surface of a red dwarf star. If you could have been there, if you could have witnessed this moment with human eyes, you would have seen a soft, warm glow surrounding you in every direction. The whole sky would have been luminous, gentle, radiant. But that light has been traveling for nearly 14 billion years. And during that time, the universe has been expanding. And when the universe expands, it stretches everything inside it, including light. The wavelengths of those photons have been pulled longer and longer over billions of years. What started as visible red light has been redshifted all the way into the microwave part of the spectrum. It's been stretched by a factor of about 1,100. That's how much the universe has grown since the moment of last scattering. Every centimeter of space has become 1,100 centimeters. Every wavelength of light has been pulled 1,100 times longer. So the light we detect today isn't the warm glow of a 3,000-degree universe. It's the cold whisper of a universe that's cooled to just 2.7 degrees above absolute zero. The afterglow stretched thin by time and expansion. There's something poignant about that. The universe in its infancy was warm and bright, and now it's ancient and cold. But the light from that warm time is still here, still reaching us, just transformed by the long, slow passage of cosmic time. Let me give you a sense of scale here. When recombination happened, when the light was freed, the universe was about 1,000th the size it is now. Everything was closer together, denser, hotter. The matter that would one day form the Milky Way galaxy was packed into a region much, much smaller than the galaxy is today. And the light escaping from that region began its journey outward. But here's the thing. While that light was traveling, the space it was traveling through was growing, expanding beneath it like a river widening as it flows. So even though light moves incredibly fast, the fastest thing there is, the journey took an almost incomprehensible amount of time because the destination kept moving away. Think of it like running on a treadmill that keeps speeding up. You're running as fast as you can, but the belt beneath you is accelerating, so you never quite get to the end. That's what it's been like for these photons. Racing through space at the speed of light, but the space itself has been stretching, elongating, growing the whole time. Some of that light is only now reaching us, not because it was slow, but because the journey was so impossibly long. And here's a question worth sitting with for a moment. Why is the light only just now arriving? If it was released 13.8 billion years ago, why didn't it get here sooner? The answer has to do with where we are, or rather, where the Earth is. When the light was freed, there was no Earth, no sun, no Milky Way, just hydrogen and helium spread across the expanding cosmos. The atoms that would one day become our solar system were scattered across vast distances, not yet drawn together by gravity. And the light that would eventually reach this spot where Earth now sits had to travel all that distance. It had to cross the growing expanse of space, and it's taken the entire age of the universe to do it. Other photons from that same moment went in other directions. Some reached other parts of space billions of years ago. Some are still traveling and won't arrive anywhere for billions of years to come. But the ones we see, the ones we detect as the cosmic microwave background, are the ones whose paths happen to intersect with our location, right here, right now. After nearly 14 billion years of travel, there's a kind of inevitability to it, a feeling that this light was always meant to arrive here at this moment. Of course, that's not true. The universe doesn't plan, but it feels meaningful nonetheless, that we tiny beings on a small planet get to witness the first light, the liberation light, the glow of the universe becoming transparent. Now, let's talk about what happened immediately after this moment of freedom. Because the universe didn't just become transparent and then sit still. It kept evolving, kept changing. After recombination, after the light was freed, the universe entered what scientists call the Dark Ages. And yes, I know I mentioned earlier that the pre-recombination universe is sometimes called the Dark Ages too. But this is a different Dark Age. This one came after the light was freed. Here's what happened. Once the electrons paired up with protons and formed neutral hydrogen, there were no more free electrons to scatter light. The universe became transparent, but it was also dark in a new way. Because there were no stars yet, no galaxies, no sources of new light. Just hydrogen gas cooling and spreading out in the expanding cosmos. The afterglow of recombination was still theirs, of course still traveling outward in all directions. But locally in any given region of space, things were getting dark, dim, quiet. For millions of years, the universe coasted like this. Transparent, but dark. Cooling, but waiting. And during that waiting period, gravity was working, slowly, patiently pulling hydrogen gas into clumps, drawing it together into denser and denser regions, building the foundations of what would become the first stars, the first galaxies. But that story comes later, much later, hundreds of millions of years later. For now, in this moment, we're exploring the moment right after recombination. The universe is in a state of transition. The light has been freed, the fog has lifted. But the next chapter hasn't started yet. It's a pause, a breath, the calm between creation and ignition. And in that calm, the photons of the cosmic microwave background began their long journey. They scattered outward from every point in space, carrying with them the imprint of the universe at 380,000 years old. And they've been traveling ever since, through the dark ages, through the formation of the first stars, through the birth of galaxies and the ignition of quasars and the slow assembly of cosmic structure. They've witnessed it all, these photons. But they don't stop. They don't pause. They just keep going. Outward, endlessly outward. There's something almost lonely about that. To be a photon born in the glow of the early universe, freed at the moment of transparency, and then just traveling forever, never stopping, never resting, just moving through the void, carrying your tiny piece of information about what the universe was like long ago. Do photons experience time? No, according to relativity. From a photon's perspective, if such a thing could exist, the journey is instantaneous, born and arrived in the same moment. But from our perspective, watching from outside the journey has taken nearly the entire age of the cosmos. Here's a thought that sometimes catches me off guard. Every photon in the cosmic microwave background has been traveling for 13.8 billion years without interacting with anything. They haven't been absorbed, haven't been scattered. They've just flown through expanding space undisturbed and uninterrupted, until now, until they reach a telescope, or a detector, or the WMAP satellite, or the Planck Observatory. And in that moment of detection, their journey ends. They deliver their message a tiny bit of information about the temperature and density of the universe at the moment they were freed, and then they're absorbed, gone, converted into a signal, a data point, a pixel in an image of the infant cosmos. It's a kind of death, I suppose, but also a kind of completion. They traveled all that way to tell us something, and we listened. So as we think about this moment of freedom, this instant when light was set free from its prison of scattering electrons, let's remember what it gave us. It gave us a window, a view into the past, a photograph of the universe at its first transparent moment. Without this event, we'd have no way to see back that far. No way to know what the early universe was really like. We'd have theories, equations, guesses, but we wouldn't have evidence. We wouldn't have light. The moment light was set free was the moment the universe became knowable. And the light from that moment is still arriving, still falling softly onto our instruments, still telling its story. But something happened to that light on its long journey, something profound. It changed. Not in its information, but in its form. The warm, visible glow of the early universe has become the cold, invisible whisper of the cosmic microwave background. And understanding how that transformation happened, how light can travel for billions of years and arrive so different from how it started, that's where we're headed now. Into the strange, beautiful physics of cosmological redshift, and the evidence it gives us that the universe is still expanding, still growing, still stretching itself into something larger than it was before. Imagine sending a letter that takes 13 billion years to arrive. A message written when nothing you recognize existed yet. No sender's address, no guarantee of delivery. Just a photon cast into the void, carrying its small piece of information across an expanding cosmos. That's what happened to the light we now call the cosmic microwave background. It began its journey when the universe was young and small and simple, and it's been traveling ever since, through cosmic dark ages and stellar births, through the formation of galaxies and the deaths of stars, through time so vast, it makes human history feel like a whisper. Tonight we're going to follow that journey, not just the distance, but the experience of it. What it means for light to travel across a universe that won't stop growing. How photons can move at the fastest speed possible and still take nearly the entire age of everything to reach us. There's a race happening, and it's been running since the beginning. Light versus expansion, speed versus distance. And neither side is winning. If you've ever thought about light traveling through space, you probably imagine it like an arrow, shot from a bow, flying straight, arriving at its target after some amount of time. And in a static universe, that's exactly what would happen. Light moves at 299,792,458 meters per second. It's fast. Unimaginably fast. At that speed, light can circle the Earth 7.5 times in a single second. It can reach the moon in just over a second, the sun in 8 minutes, the nearest star in about 4 years. So, you'd think that light released 13.8 billion years ago would have traveled 13.8 billion light years and stopped. Job done. Journey complete. But the universe doesn't work that way, because space itself is expanding, and when space expands, it stretches everything inside it, including the distance light has to travel. So even though photons are moving as fast as physics allows, the finish line keeps moving away from them. It's like running toward a horizon that recedes as you approach. You're making progress, you're moving, but the destination is also moving, farther and farther into the distance. This is one of the most beautiful and counterintuitive ideas in all of cosmology. The universe isn't expanding into anything. There's no edge it's pushing against. Space itself is growing. The fabric of reality is stretching, and everything embedded in that fabric, galaxies, clusters, voids, and yes, photons of light, is being carried along for the ride. Let me give you an analogy that might help. Imagine you're an ant walking along a rubber band. You're moving at a steady pace, one step at a time, heading from one end of the rubber band to the other. But while you're walking, someone is stretching the rubber band, slowly pulling it longer. Now, from your perspective as the ant, you're still moving forward. You're still making progress, step by step. But the rubber band is getting longer, so the distance to your destination is increasing even as you walk. If the rubber band stretches slowly enough, you'll eventually reach the other end, but it will take you much longer than you'd expect. And if the rubber band stretches too fast, you might never get there at all. You'd walk forever, always moving forward, but never quite arriving. That's what it's like for light traveling through an expanding universe. The photons are moving, always moving, but the space they're traveling through is stretching, so the journey takes longer than it would in a static cosmos. Much longer. Now here's where it gets interesting. When the cosmic microwave background photons were released when they escaped at the moment of recombination, the universe was small, about 1,000th the size it is now. The region of space that would one day become the observable universe was compressed into a volume much, much smaller than it is today. And the light that was freed from that small, dense, hot region began traveling outward. But as it traveled, the universe grew, expanded, stretched. And the photons, even though they were moving at the speed of light, found themselves in a race they couldn't win. The space ahead of them was growing faster than they could cross it. For billions of years, these photons have been journeying through expanding space. And here's the thing, some of them are only just now reaching us. Not because they've been moving slowly. They've been moving at the speed of light the entire time. But because the distance they had to cross kept growing while they were crossing it. Scientists have a way of measuring this. They talk about something called co-moving distance versus light travel distance. Light travel distance is simple. It's how far light can travel in a given amount of time. If light has been traveling for 13.8 billion years, then the light travel distance is 13.8 billion light years. Easy. But co-moving distance is different. It takes into account the expansion of space. It measures how far away something is, now accounting for all the stretching that's happened since the light was emitted. And when you do the math, when you calculate the co-moving distance to the surface of last, scattering the place where the CMB photons were released, you get a number much larger than 13.8 billion light years. You get about 46 billion light years. That's how far away the region that emitted the CMB is now. Not because the photons traveled that far, but because space has been expanding the whole time they've been traveling. The starting point and the destination have been moving apart, and the photons have been caught in the middle, racing across the growing gap. Does that make sense? It's one of those ideas that feels slippery at first. But sit with it for a moment. Imagine the universe as a grid. Each square on the grid represents a region of space. Now imagine that over time, each square gets bigger. The grid stretches. The distance between any 2 points increases, not because anything moved through the grid, but because the grid itself expanded. That's what's happening with space. The cosmic grid is stretching, and light is traveling across that stretching grid, moving from square to square, while the squares themselves grow larger. Here's another way to think about it. If you could somehow freeze the expansion of the universe right now, if you could stop space from growing and measure the distance from here to the place where the CMB was emitted, you'd find it's about 46 billion light years away. But the light from that place has only been traveling for 13.8 billion years. So how did it get here if the distance is so much greater than the travel time would suggest? The answer is that when the light started its journey, the distance was much smaller. The universe was much smaller, and as the light traveled, the distance grew beneath it. It's been chasing a moving target, and only now, after all this time, has it finally caught up. There's something both frustrating and beautiful about this. Light is the fastest thing in the universe. Nothing can outrun it, but space doesn't have to outrun it. Space just has to grow. And by growing it, can stretch the journey into something far longer than speed alone would suggest. Now, let's talk about what this means for the photons themselves. Because from a photon's perspective, if we can even use that word, the journey is different. According to Einstein's theory of relativity, time slows down the faster you move, and at the speed of light, time stops altogether. So for a photon traveling at light speed, no time passes. From its perspective, if such a thing makes sense, it's emitted and absorbed in the same instant. There is no journey, no waiting, no sense of duration. The photon is born at the surface of last scattering and arrives at a telescope on Earth in what feels to the photon like zero time. But from our perspective, watching from outside, the journey takes 13.8 billion years. We see the photon crossing vast distances. We see it traveling through the dark ages past, forming galaxies through clusters and voids. We see it experiencing time. But the photon itself experiences nothing. It exists in a kind of eternal now, a state where beginning and ending are simultaneous. Isn't that strange? Two perspectives on the same journey, one where billions of years pass, one where no time passes at all, both true, both valid, just seen from different frames of reference. And here's something else to consider. The photons we detect today as the cosmic microwave background aren't special. They're not the only ones that were released at recombination. Every point in space at the moment, the universe became transparent, released photons in all directions. And those photons have been traveling ever since. Some of them reached Earth billions of years ago, passed right through the region where our planet now sits, and continued on into the depths of space. Others are still on their way traveling toward us from regions of the universe we can't see yet. The CMB we detect today is just the subset of photons whose paths happen to intersect with Earth right now, at this moment in cosmic time. And here's the beautiful part. If you could somehow transport yourself to a different galaxy, billions of light years away, you'd still see the cosmic microwave background. But it wouldn't be the same photons. It would be different photons emitted from different regions of space that happen to be arriving at that galaxy at this moment. The CMB is everywhere. It's isotropic, as scientists say, the same in all directions, because it was emitted from everywhere at the same cosmic time, and it's been traveling ever since. So, in a sense, the universe is full of overlapping spheres of light. Each point in space sits at the center of its own sphere of CMB photons, arriving from all directions. And each sphere is slightly different, made up of different photons from different regions of the early universe. But they all tell the same story. They all carry the same message. The universe was once hot, dense, and opaque. And then it became cool enough to be transparent. And the light from that moment is still traveling. Have you ever wondered what happened to the photons that didn't come toward us? The ones that went in other directions. They're still out there, still traveling, heading toward regions of space so far away that we'll never see them, never know about them. And in those distant regions, perhaps there are observers. Perhaps there are beings looking at their own cosmic microwave background, detecting their own set of ancient photons and wondering the same things we wonder. What does this light mean? Where did it come from? What can it teach us? We'll never meet those observers if they exist. The expansion of space ensures that. But it's comforting in a way to think that the CMB is being observed from countless different vantage points across the cosmos. That the story it tells, the story of the universe becoming transparent, is being read in infinite variations, each one slightly different, but all fundamentally the same. Now, there's a detail I want to share with you. A piece of this story that often gets overlooked, The photons we detect as the CMB haven't just been traveling, they've been alone. For 13.8 billion years, most of these photons haven't interacted with anything. They haven't been absorbed by gas, they haven't scattered off dust. They've just flown straight and true through the expanding void, undisturbed, unaltered, carrying their original information about the early universe. That's remarkable when you think about it. Space is not perfectly empty. There's gas out there, dust, the occasional stray atom. And yet these photons have managed to avoid all of it. They've threaded the needle between obstacles traveling across billions of light years of space without hitting anything significant enough to stop them, until now. Until they encounter Earth's atmosphere, or a satellite's detector, or the mirror of a telescope. And in that moment, after nearly 14 billion years of solitude, they finally interact. They're absorbed, measured, turned into data. It's the end of a long, quiet journey, but also the fulfillment of a kind of purpose. Because without that final interaction, without being detected, the photon's information would remain unknown. It would just keep traveling forever, carrying a message no one reads. So, here's the thing about this journey. It's not just about distance. It's not just about time. It's about persistence. These photons have been traveling longer than stars have lived, longer than galaxies have existed in their current forms. They've outlasted almost everything, and they're still here, still arriving, still delivering their message about what the universe was like at 380,000 years old. And that message is about to become clearer, because the journey, as long as it's been, is only part of the story. The photons didn't just travel, they changed. They were stretched by the expansion of space, transformed from visible light into microwaves. And that transformation, that redshift, is one of the most important pieces of evidence we have for understanding the universe itself. It tells us not just that the universe is expanding, but how fast. It tells us about the shape of space, the history of cosmic growth, the future that awaits. So as we move forward, as we continue to follow this ancient light, we're going to explore what happened to these photons during their long journey, how they changed, why they changed, and what that change reveals about the cosmos we live in. There's a kind of alchemy happening in the universe, not the medieval dream of turning lead into gold, but something quieter, more patient. The transformation of warm, visible light into cold, invisible whispers. When the cosmic microwave background was born, it glowed with the color of embers, deep red, orange, warmth you could almost feel. But today, nearly 14 billion years later, that same light arrives as microwaves, invisible to our eyes, undetectable without special instruments. The light hasn't disappeared, it's just been stretched, pulled thin by the expansion of space itself. And in that stretching and that transformation lies one of the most profound pieces of evidence we have, that the universe is growing. Tonight we're going to explore why ancient starlight arrives as radiostatic, why the universe's first glow has become a whisper we can only hear with machines, and what this tells us about the journey light takes through an expanding cosmos. The answer is written in wavelengths, in the space between crests, in the way reality itself can stretch. When light travels through expanding space, something remarkable happens. The light gets stretched along with the space. Imagine a wave drawn on a rubber band. If you pull the rubber band, making it longer, the wave stretches too. The distance between peaks increases. The wavelength grows. And when a wavelength grows, the energy of the light decreases. It becomes redder, cooler, less energetic. This is what scientists call cosmological redshift. And it's different from other kinds of redshift you might have heard about. It's not caused by motion through space like the Doppler shift you hear when an ambulance passes. It's caused by the expansion of space itself, the stretching of the fabric of reality. When the CMB photons were released at recombination, when they escaped from the opaque plasma and began their journey, they had a wavelength of about 1 micrometer. That's in the infrared range, just barely into the visible spectrum. The universe at 3,000 degrees. Kelvin glows in deep reds and oranges like a cooling coal. If you could have seen it with human eyes, it would have looked dim but warm. A soft, pervasive glow surrounding you in every direction. Not bright like daylight, more like twilight. The dying light of a sunset that covers the entire sky. But that was then. And between then and now, the universe has grown. Space has expanded by a factor of about 1,100. Every centimeter has become 1,100 centimeters. Every meter has become 1,100 meters. Every light year has become 1,100 light years. And crucially, every wavelength of light traveling through that space has been stretched by the same factor. So, the photons that started with a wavelength of 1 micrometer now have a wavelength of about 1 millimeter. That's 1,000 times longer. And 1 millimeter is firmly in the microwave range of the electromagnetic spectrum. It's the same kind of radiation your microwave oven uses to heat food, though much, much weaker. The CMB photons have so little energy now that they barely interact with anything. They pass through matter almost unnoticed. They've been diluted by expansion, stretched thin across the cosmos. Here's how scientists measure this stretching. They use something called the redshift parameter, usually written as the letter Z. It's a number that tells you how much the universe has expanded since the light was emitted. For the cosmic microwave background, Z is approximately 1,100. That means the universe is 1,100 times larger now than it was when the CMB was released. And the wavelengths of the CMB photons are 1,100 times longer. It's a direct measurable connection between the expansion of space and the transformation of light. Think about what this means. Every photon in the CMB carries within it a record of cosmic expansion, not written in words or numbers, but encoded in its wavelength. By measuring how much the light has been stretched, we can calculate how much the universe has grown. We can work backward from the microwaves we detect today to figure out what the universe was like when that light was emitted. We can measure the temperature, the density, the age, all from the color of ancient light. And here's the beautiful part. The stretching is still happening. Right now, as these photons travel toward us, as they cross the final light years before reaching Earth, they're still being pulled to longer wavelengths. The universe is still expanding, space is still growing, and the light is still transforming. By the time a CMB photon enters a detector on one of our satellites, it's been stretched just a little bit more than it was a moment ago. The process never stops. It's continuous, relentless. The universe breathing outward and light stretching with each breath. Now, let's talk about temperature. Because the wavelength of light is directly related to temperature, hot objects emit short wavelength light, blue, ultraviolet, X-rays. Cool objects emit long wavelength light, red, infrared, microwaves. The CMB, when it was emitted, had a temperature of about 3,000 degrees Kelvin. That's the temperature of the surface of a red dwarf star, hot enough to melt any metal you can think of. Hot enough to glow visibly. But today, after being stretched by a factor of 1,100, the CMB has a temperature of just 2.725 degrees Kelvin. That's 2.725 degrees above absolute zero, minus 270.4 degrees Celsius, minus 454.8 degrees Fahrenheit. It's one of the coldest things in the universe. Colder than the space between stars, colder than the voids between galaxies. The only things colder are objects that have been artificially cooled by humans in laboratories or certain rare cosmic phenomena. So, the universe's first light, which began as warmth, has become cold. Not because the photons lost energy to friction or collisions they didn't, but because the space they're traveling through has grown so much that their wavelengths have been pulled to the point where they carry almost no energy at all. They're ghosts of their former selves, echoes of warmth stretched into whispers of cold. Here's an analogy that might help. Imagine you're playing a note on a guitar string, a high note. The string vibrates quickly with a short wavelength. Now, imagine that While the note is still sounding, someone slowly lengthens the string, pulls it tighter, stretches it. As the string gets longer, the wavelength of the vibration increases. The note drops in pitch, gets lower, deeper. If you stretch the string enough, the note would eventually become so low that you couldn't hear it anymore. It would drop below the range of human hearing into infrasound. The vibration would still be there, still moving through the string, but you'd need special equipment to detect it. That's what's happened to the light of the CMB. It started as a note we could see visible light and has been stretched into a note we can only detect with radio antennas and microwave receivers. And just like that guitar string analogy, the stretching tells us something important. It tells us that space is expanding, because if space weren't expanding, if the universe were static, the light would arrive at the same wavelength it was emitted. There'd be no redshift, no transformation. The CMB would still be glowing in the infrared and visible range. We'd see it with our eyes as a faint orange glow covering the sky. But we don't. We see it as microwaves. And that difference, that transformation from visible to microwave, is direct evidence that the universe has been growing for billions of years. Now here's something that often confuses people, a common misconception. Some people think redshift means the light is moving away from us, that the photons themselves are receding like a car driving into the distance. But that's not quite right. The photons are moving toward us. They've been traveling toward us for 13.8 billion years. They're not receding, they're arriving. But the space they traveled through has been expanding, and that expansion stretched the light. So it's not the motion of the light that causes the redshift. It's the growth of space itself. Let me give you another way to think about it. Imagine you send a letter across the ocean. While the letter is in transit, the ocean grows wider. The letter still reaches its destination, it's still moving toward you. But the journey took longer than expected because the ocean expanded while the letter was crossing it. And when the letter arrives, it's a little faded, a little worn. Not because the letter itself changed, but because the journey was longer and harder than it would have been in a static ocean. That fading, that wear is like the redshift. The letter is the photon. The ocean is space. And the expansion is what stretches the light. There's also a beautiful symmetry here. The amount of redshift tells us not just how much space has expanded, but also how old the light is. The more redshifted something is, the farther back in time we're seeing it. And the CMB has the highest redshift of anything we can observe, a redshift of about 1,100. That means it's the oldest light we can detect, the farthest back in time we can see. Everything with a higher redshift would have been emitted before recombination, when the universe was still opaque. And we can't see that. It's hidden behind the wall of fog. The CMB is the edge of the visible universe, the boundary between what we can observe and what we cannot. Think about that for a moment. We're looking at the oldest possible light, the first light that could travel freely. There's nothing older we could ever hope to see, at least not with light. Because before the CMB, the universe was dark to photons, opaque, unseeable. So, when we study the cosmic microwave background, we're studying the limit, the furthest edge of observability, the beginning of transparency itself. And the fact that this light has been stretched into microwaves is not an inconvenience. It's not a limitation. It's a gift. Because the stretching tells us so much. It tells us how old the universe is, how much it's expanded, how fast it's been growing. The transformation from visible light to microwaves is a measurement tool, a cosmic ruler, a way of reading the history of expansion written in wavelengths. Here's a specific example. By measuring the temperature of the CMB, today 2.725 Kelvin, and knowing what the temperature was when it was emitted about 3,000 Kelvin, we can calculate the redshift. We can determine that the universe has expanded by a factor of about 1,100. And from that, we can work out other things, like the age of the universe at recombination, 380,000 years, or the current size of the observable universe, about 93 billion light years in diameter, all from the color and temperature of ancient light. It's almost like the photons are carrying a timestamp, a record of when they were born and how much the universe has changed since then. And we can read that timestamp by measuring their wavelength, by seeing how much they've been stretched. Now I want you to imagine what the CMB would look like if we could see microwaves with our eyes, if our retinas were sensitive to wavelengths around 1 millimeter instead of the much shorter wavelengths of visible light. What would we see? We'd see a glow, a faint uniform glow covering the entire sky, not localized to any one spot, not coming from a particular direction, just everywhere, omnipresent, isotropic, a soft, even light that fills the heavens. And if we looked closely, if our eyes were sensitive enough, we'd see tiny variations, hot spots and cool spots, temperature differences of only a few millionths of a degree, ripples in the glow, patterns in the light. But we can't see microwaves. Our eyes aren't built for it. So instead, we use instruments, radio telescopes, satellites with microwave detectors, antennas tuned to the right frequencies, and these instruments paint a picture for us. They translate the invisible into something we can understand. Maps of the CMB, false color images where blue represents slightly cooler regions and red represents slightly warmer ones. And when we look at those maps, we're seeing the universe as it was 380,000 years after the Big Bang. We're seeing the seeds of galaxies, the fingerprints of cosmic structure, the earliest patterns in the fabric of space and time. All of this is possible because light stretches, because the universe expands, because photons carry within them a memory of how far they've traveled and how much the cosmos has grown since their birth. There's something almost poetic about it. The universe is telling us its story in the language of wavelengths, in the color of light. And by learning to read that language, by understanding how redshift works, we've unlocked the ability to see back to the beginning, to witness the first moments of transparency, to measure the expansion of everything. And this is just the start. Because the stretching of light doesn't just tell us about the past, it tells us about the present, and even the future. The rate at which the universe is expanding now can be measured by looking at redshift. And when we do that, when we measure carefully, we discover something surprising, something that changed our understanding of the cosmos entirely. The expansion isn't slowing down, it's speeding up, accelerating, driven by something we don't fully understand, something we call dark energy. But we'll get to that, because the story of the CMB is also the story of what it reveals, the hidden truths it exposes, the mysteries it points to. And those revelations are waiting for us as we continue. The maps made by satellites, the patterns in the ancient light, the secrets written in temperature variations so small they almost weren't detected at all. Imagine trying to photograph something that fills the entire sky. Not a landscape, not a constellation, but everything. Every direction at once. A portrait of the whole universe taken at a single moment in time. That's what scientists set out to do when they began mapping the cosmic microwave background. They wanted to see the infant universe, to capture its face, to read the patterns written in ancient light. And over the course of 3 decades, through 3 remarkable satellite missions, they succeeded. They created the most important baby picture ever taken, a photograph of everything when it was just 380,000 years old. Tonight we're going to explore those missions. COBE, WMAP, Planck. 3 telescopes launched into space to stare at invisible light. 3 generations of technology, each one revealing finer details, subtler patterns, deeper truths. And what they found changed everything we thought we knew about the cosmos. The universe, it turns out, has freckles, tiny imperfections that became galaxies. The story begins in the late 1980s. By that time, scientists knew the cosmic microwave background existed. Penzias and Wilson had detected it back in 1964. But detecting it and mapping it are 2 very different things. Detection just tells you the light is there. Mapping tells you what it looks like, where it's warmer, where it's cooler, what patterns exist in its glow. And those patterns scientists suspected would be incredibly important. Because if the early universe was perfectly smooth, perfectly uniform, then structure couldn't have formed. Galaxies wouldn't exist. Stars wouldn't exist. We wouldn't exist. There had to be variations, tiny differences in density, small fluctuations in temperature, seeds that gravity could pull on drawing matter together into clumps that would eventually become cosmic structure. But here's the problem. Those variations, if they existed, would be incredibly small. Temperature differences of only a few parts in 100,000. Finding them would be like trying to detect a single degree of difference in temperature across an entire football field. You'd need extraordinary precision, extraordinary sensitivity, and you'd need to do it from space because Earth's atmosphere glows in the microwave range. It would drown out the signal like trying to see stars at noon. So in November of 1989, NASA launched COBE, the Cosmic Background Explorer, a satellite designed to do one thing: map the CMB with unprecedented accuracy. COBE carried 3 instruments, but the one that mattered most for this story was called the Differential Microwave Radiometer, DMR for short. And DMR was built to measure temperature variations in the cosmic microwave background across the entire sky. For 4 years, COBE orbited Earth, slowly scanning the heavens, collecting data. And in 1992, the team released their first results. They held a press conference, showed images, and what they revealed was stunning. The CMB wasn't perfectly smooth. It had structure, tiny hot spots and cool spots scattered across the sky. Temperature variations of about 1 part in 100,000. Exactly what the theories predicted. Exactly what was needed for galaxies to form. George Smoot, one of the lead scientists on the COBE team, famously described the discovery as seeing the face of God. Not in a religious sense, but in the sense of witnessing something fundamental, something profound. The seeds of everything that would come after, the fingerprints of creation itself. And for that work, for confirming that the early universe had structure, Smoot and another scientist named John Mather won the Nobel Prize in Physics in 2006. But COBE's map was blurry, low resolution. It could see the big picture, but not the fine details. The variations it detected were real, but they were smoothed out over large patches of sky. It was like looking at a photograph taken with an old camera. You could see shapes, but not features. You could tell there was structure, but you couldn't read it clearly. Scientists needed more. They needed sharper vision, higher resolution. A map that could reveal not just that variations existed, but what those variations actually looked like in detail. So in 2001, NASA launched WMAP, the Wilkinson Microwave Anisotropy Probe, named after David Wilkinson, a physicist who had dedicated much of his life to studying the CMB and who passed away shortly before the satellite launched. WMAP was sent not to orbit Earth, but to a special location in space called the L2 Lagrange point, about 1 million miles from Earth in the opposite direction from the Sun. At L2, the gravitational pulls of the Earth and Sun balance out in such a way that a spacecraft can stay relatively stationary with minimal fuel. It's the perfect place to observe the sky without interference. Cold, dark, stable. WMAP carried sensors far more sensitive than COBE's. It could measure temperature variations down to 1 part in 1 million. And over the course of 9 years, from 2001 to 2010, it scanned the entire sky, repeatedly building up an incredibly detailed map of the cosmic microwave background. And that map was revolutionary. WMAP didn't just confirm what COBE had found. It refined it, sharpened it, revealed structure that COBE couldn't see. The hot spots and cool spots weren't random, they had a pattern. A size distribution. Scientists could measure the sizes of the fluctuations, and from those measurements they could extract information about the early universe. How old it was, what it was made of, how fast it was expanding. WMAP turned the CMB from a curiosity into a precision tool, a way of measuring cosmology with accuracy that had never been possible before. One of the most important things WMAP did was determine the age of the universe. By analyzing the patterns in the CMB, by measuring the sizes and shapes of the temperature fluctuations, scientists calculated that the universe is 13.77 billion years old. Give or take about 60 million years. That's an error margin of less than 0.5%. Extraordinary precision. And it came from light. From the patterns in ancient glow, WMAP also measured the composition of the universe. And this is where things get strange. Because when you add up all the matter and energy in the cosmos, you find that normal matter, the stuff that makes up stars and planets and people, accounts for less than 5% of the total, just 4.6%. The rest is something else. About 24% is dark matter, a form of matter that doesn't emit light and doesn't interact with normal matter, except through gravity. We can't see it directly. We only know it's there because of its gravitational effects. And the remaining 71% is dark energy, a mysterious force that's causing the expansion of the universe to accelerate. We don't know what dark energy is. We can barely describe it. But WMAP measured it, quantified it, showed us that the universe we see is just a tiny fraction of what actually exists. Think about that. By studying the oldest light in the universe, we discovered that most of the universe is invisible, hidden, made of things we don't understand. That's both humbling and exciting. It means there's so much more to learn, so much more to discover. But even WMAP wasn't the end of the story, because as good as its map was, there were still details it couldn't resolve, still questions it couldn't answer. So in 2009, the European Space Agency launched Planck, the most advanced CMB satellite ever built. Named after Max Planck, the physicist who helped lay the foundations of quantum mechanics. And Planck was designed to create the definitive map of the cosmic microwave background, the sharpest, the most detailed, the final word at least for this generation of technology. Planck, like WMAP, was sent to the L2 Lagrange point, but it carried instruments even more sensitive, even more precise. It could measure temperature variations down to a few millionths of a degree. And it didn't just look at temperature, it also looked at polarization, the way light waves are oriented as they travel through space. Polarization carries additional information. It can tell you about the processes that created the light, the forces that shaped it. And by measuring polarization, Planck was able to extract insights that previous missions couldn't. For 4 years, from 2009 to 2013, Planck scanned the sky. And when the data was processed, when the map was finally revealed, it was breathtaking. Every detail, every ripple, every tiny fluctuation in the ancient light captured with stunning clarity. The Planck map of the CMB is one of the most important scientific images ever created. It's a snapshot of the universe at 380,000 years old. A portrait of the infant cosmos. And it's beautiful. When you look at the Planck map, you see a modeled pattern. Regions of slightly warmer and slightly cooler light, colored in false hues, red for warm, blue for cool, spread across the sky like paint on a canvas. The variations are tiny, just a few hundred millionths of a degree, but they're real and they matter, because those tiny variations are the seeds. The places where hundreds of millions of years later, matter would begin to clump together, where galaxies would form, where stars would ignite, where planets would coalesce. Everything you see in the universe today, every galaxy cluster, every supercluster, every cosmic web of structure, it all started as a tiny temperature fluctuation in the cosmic microwave background. Planck confirmed what WMAP had measured, but with even greater precision. The universe is 13.8 billion years old. It's composed of roughly 68% dark energy, 27% dark matter, and 5% normal matter. It's geometrically flat, meaning the overall curvature of space is essentially zero. and it's expanding at a rate of about 67 kilometers per second per megaparsec. That's a measure of how fast distant galaxies are receding from us due to the expansion of space. All of this encoded in the patterns of ancient light. But here's the thing that really amazes me. These maps, COBE, WMAP, Planck, they're not just pretty pictures, they're data, measurements. Every pixel in those images represents a temperature reading from a specific direction in the sky. And by analyzing those readings, by studying the statistical properties of the fluctuations, scientists can test theories. They can compare predictions to observations. They can see if the universe behaves the way they think it should. And what they've found is remarkable. The patterns in the CMB match the predictions of a theory called inflation almost perfectly. Inflation is the idea that the universe in the first fraction of a second after the Big Bang underwent a period of exponential expansion. It grew faster than the speed of light, driven by a strange form of energy that existed only in those earliest moments. And that rapid expansion stretched tiny quantum fluctuations into macroscopic variations in density. Those variations frozen into the fabric of space are what we see today as the hot spots and cool spots in the CMB. Inflation sounds wild. It sounds almost like science fiction. But the patterns in the CMB support it. The sizes and shapes and distribution of the fluctuations are exactly what inflation predicts. It's one of the strongest pieces of evidence we have that something very strange happened in the first moments of the universe. There's also another pattern in the CMB that's incredibly important. Scientists call them acoustic peaks. Remember earlier when I mentioned that before recombination, the universe was filled with sound waves, pressure waves moving through the plasma? Well, those sound waves left an imprint. When the plasma turned into neutral gas and the light was freed, the waves got frozen into the CMB. And when we analyze the temperature fluctuations, we can see those waves. We can measure their size. And from that, we can learn about the density of the universe, the amount of normal matter, the amount of dark matter, even the geometry of space itself. It's like listening to a bell that rang nearly 14 billion years ago. The sound is long gone, but the vibrations are still there encoded in light. And by studying those vibrations, we can reconstruct what the universe was like when it was young. Here's a specific example. One of the acoustic peaks in the CMB tells us about the density of normal matter, protons, neutrons, electrons. The height and position of that peak depend on how much matter there was in the early universe. And when scientists measured it, they found something surprising. The amount of normal matter in the universe today matches almost exactly the amount predicted by Big Bang nucleosynthesis, the process that created hydrogen and helium in the first few minutes. Two completely independent measurements separated by billions of years and entirely different physical processes agree with each other. That's not a coincidence. That's confirmation. That's the universe telling us we're on the right track. There's a lesson here, I think, about patience, about precision, about the value of looking carefully at things that seem simple. The CMB is just light, just photons traveling through space. But by studying it, by measuring it with incredible care, by building satellites and launching them into space, by spending years collecting data and analyzing it, we've unlocked secrets about the universe's birth, its composition, its fate. We've learned that the cosmos is stranger and more wonderful than we imagined, that most of it is invisible, that it started in a state almost incomprehensibly hot and dense, and has been cooling and expanding ever since. And all of this from a faint glow in the microwave range, from light so old it was born before stars existed. Do you ever wonder what it would be like to work on one of these missions? To spend years of your life building instruments, calibrating sensors, processing data, just to create a map of invisible light. It takes a kind of faith, I think. A belief that the universe is knowable, that if you ask the right questions and look carefully enough, reality will answer. And in the case of the CMB, it did. The universe showed us its face, its infant face, and we got to see it. The maps made by Kobe W. Map and Planck are more than scientific achievements. They're milestones. Proof that humans, despite our brief existence and tiny size, can understand the cosmos. We can reach back across billions of years. We can see the beginning. We can read the story written in light. But those maps reveal more than just the past. They point toward mysteries, questions we still don't have answers for. What is dark matter? What is dark energy? Why does the universe have the geometry it does? Why are the fluctuations in the CMB distributed the way they are? And as we explore what those ripples in ancient light tell us, we're going to encounter some of the deepest puzzles in all of science. The invisible forces shaping the cosmos. The hidden architecture of reality itself. Most of what exists is invisible, not hidden behind clouds or buried underground, but fundamentally unseeable, made of substances that don't emit light, don't reflect it, don't interact with it in any way we can directly observe. For most of human history, we didn't know this. We thought the universe was made of the things we could see: stars, planets, gas, dust. But then we looked more carefully at the oldest light in the cosmos. We studied the tiny ripples in the cosmic microwave background. And those ripples told us something startling. The universe we see, everything made of atoms, everything that glows or reflects or absorbs light, is just a small fraction of what's actually out there, about 5%. The rest is shadow, mystery, forces and matter we're only beginning to understand. Tonight we're going to explore what the patterns in ancient light reveal about the invisible universe, about dark matter that shapes galaxies without shining, about dark energy that's pulling space apart, about a cosmos far stranger than the one our eyes show us. The ripples in the CMB are more than features. They're measurements, encoded messages about what the universe is made of. Let's start with something that sounds simple but isn't: the shape of the universe. When scientists talk about the geometry of space, they're asking a fundamental question. Is the universe flat? Does it curve inward like the surface of a sphere? Or does it curve outward like a saddle? These aren't abstract mathematical curiosities. They're real physical properties of space itself. And they matter because the geometry of the universe determines its fate. A universe that curves inward will eventually stop expanding and collapse back on itself in a big crunch. A universe that curves outward will expand forever, growing colder and more dilute until nothing remains but scattered particles in an infinite void. A flat universe sits right on the edge. It will expand forever, but more slowly, gradually cooling, gradually dimming, approaching, but never quite reaching a state of complete stillness. So, which is it? For decades, scientists didn't know. They had theories, predictions, but no direct measurement. And then they looked at the CMB. Specifically, they looked at the sizes of the hot spots and cool spots in the ancient light. Because here's the thing, the size of those fluctuations depends on the geometry of space. In a flat universe, the fluctuations have a certain characteristic size, about 1 degree across on the sky. In a curved universe, that size would be different. Larger if space curves inward, smaller if it curves outward. It's like looking at an object through a lens. The lens bends light, distorting the image. Space can do the same thing. Its curvature affects how we see distant objects, including the patterns in the CMB. When WMAP measured the sizes of the fluctuations, when Planck refined those measurements even further, they found something remarkable. The universe is flat. Not perfectly flat. Nothing in nature is perfect, but flat to within 1%. The curvature, if it exists at all, is so small we can't detect it. Space on the largest scales appears to be geometrically flat, like an infinite sheet extending in all directions. No edges, no boundaries, just space going on and on. Now you might wonder why this matters. Why does the shape of space tell us anything important? The answer has to do with density. The geometry of the universe is determined by how much matter and energy it contains. If there's too much gravity, we'll eventually overcome the expansion and pull everything back together. The universe will curve inward. If there's too little, the expansion will continue forever without slowing. The universe will curve outward. But there's a special amount, a critical density where the geometry is exactly flat, where the expansion continues forever, but just barely. And the fact that the universe is flat tells us it has almost exactly that critical density. But here's where it gets strange. When you add up all the normal matter in the universe, all the atoms, all the gas, all the stars, you get only about 5% of the critical density. That's not enough to make the universe flat, not even close. So, where's the rest? What's providing the other 95%? The answer comes in two parts: dark matter and dark energy. And the CMB reveals both. Let's talk about dark matter first. Dark matter is a form of matter that doesn't emit light, doesn't absorb it, doesn't reflect it. It's completely invisible to telescopes. We can't see it directly, but we know it's there because of its gravitational effects. Galaxies spin faster than they should based on the visible matter alone. Galaxy clusters hold together more strongly than normal matter can account for. And when light from distant objects passes near massive structures, it gets bent by gravity in ways that require far more mass than we can see. Dark matter was first proposed in the 1930s by a Swiss astronomer named Fritz Zwicky. He was studying the Coma cluster, a group of galaxies bound together by gravity, and he noticed something odd. The galaxies were moving too fast. Based on the amount of visible matter in the cluster, they should have flown apart long ago. But they hadn't. Something was holding them together, something with mass, something generating gravity, but something invisible. Zwicky called it dark matter. And for decades, the idea was largely ignored. It seemed too strange, too unlikely. But as more evidence accumulated, as more observations confirmed that galaxies behave as if they contain far more mass than we can see, the idea became unavoidable. Dark matter is real. It's out there. We just can't see it with light. And the CMB confirms this in a beautiful way. Remember those acoustic peaks I mentioned earlier? The patterns in the CMB created by sound waves in the early universe. Well, those patterns are sensitive to the amount of matter present when the waves were traveling. Normal matter atoms interacts with light. It creates pressure. It affects how the waves move. Dark matter, on the other hand, doesn't interact with light. It only interacts through gravity, so it affects the waves differently. By measuring the heights and positions of the acoustic peaks, scientists can separate the effects of normal matter from the effects of dark matter. They can weigh the universe. And what they find is that dark matter outweighs normal matter by about 5 to 1. For every kilogram of atoms, there are roughly 5 kilograms of dark matter. Invisible, silent, but undeniably present. Think about what that means. Most of the matter in the universe is made of something we've never directly detected, something that doesn't fit into the standard model of particle physics, something that might be a new kind of particle entirely. Scientists have been searching for dark matter particles for decades. They've built detectors deep underground to shield them from cosmic rays. They've looked for signals of dark matter colliding with normal matter. They've searched for the faint glow that might be produced when dark matter particles annihilate each other. So far, nothing. Dark matter remains elusive, but its effects are everywhere, shaping galaxies, holding clusters together, leaving imprints in the oldest light. Now, dark energy. This is even stranger. Dark energy isn't matter at all. It's a property of space itself, a kind of energy that exists even in the vacuum. And it has a very strange effect. It causes space to expand. Not just to allow expansion, but to actively drive it, to push galaxies apart. And the more space you have, the more dark energy there is. So as the universe expands, dark energy becomes more and more dominant, and the expansion accelerates. This was a shocking discovery. For most of the 20th century, scientists assumed the expansion of the universe was slowing down. Gravity, after all, pulls things together. So it should be putting the brakes on expansion, gradually slowing it over time. But in 1998, two teams of astronomers studying distant supernovae found something unexpected. The expansion isn't slowing down, it's speeding up. Galaxies far away are receding faster than they should be if gravity were the only force at play. Something is pushing them. Something is making space expand faster and faster. And that something is dark energy. The CMB provides evidence for dark energy too. By measuring the patterns in the ancient light, by analyzing how those patterns have been affected by the geometry and expansion history of the universe, scientists can determine how much dark energy there is. And the answer is about 68% of the total energy density of the cosmos. Dark energy dominates. It's the largest component of the universe. And yet, we have no idea what it is. Some scientists think dark energy is the cosmological constant, a term Einstein introduced into his equations and later called his greatest blunder. The cosmological constant represents a fixed energy density of empty space, a kind of baseline energy that exists everywhere always. Others think dark energy might be something more dynamic, something that changes over time, a field like the electromagnetic field, but one that pervades all of space and exerts a repulsive force. We don't know yet. The nature of dark energy is one of the biggest unsolved mysteries in physics. But here's what we do know, thanks to the CMB. The universe is composed of approximately 5% normal matter, 27% dark matter, and 68% dark energy. That's the cosmic pie chart, the inventory of everything. And it's wildly different from what we expected. The stuff we're made of, atoms, molecules, the matter that makes up stars and planets and people, is just a tiny sliver of the whole. The universe is mostly invisible, mostly unknown. There's something humbling about that. We walk around thinking the world is made of the things we can touch and see: rocks, water, air, light. But the truth is, we're surrounded by substances we can't perceive. Dark matter is passing through you right now. Millions of particles every second streaming through your body without interacting, without leaving a trace. And dark energy is pulling space apart beneath your feet, slowly, imperceptibly, but relentlessly. The universe is stranger than our senses can tell us. And all of this was revealed by studying tiny temperature variations in ancient light, by looking at ripples that are only a few hundred millionths of a degree in size, by analyzing patterns so subtle they almost weren't detected. The CMB is a treasure map, and the treasure is knowledge, understanding, insight into the fundamental nature of reality. Let me give you a specific example of how this works. One of the acoustic peaks in the CMB, the first peak, the tallest one, tells us about the total density of the universe. The height of that peak depends on how much matter and energy there is. Too much, and the peak is higher. Too little, and it's lower. By measuring the peak precisely, scientists can determine that the universe has almost exactly the critical density. It's flat, balanced on the edge between collapse and eternal expansion. But normal matter alone doesn't provide enough density. So, there must be something else. And when scientists look at the other peaks, the second and third and fourth peaks, they can tease apart the contributions. The second peak is sensitive to the ratio of normal matter to dark matter. The third peak tells you about the geometry of space. Each peak is a piece of the puzzle, a clue. And when you put them all together, you get a picture of the universe's composition. 5% normal matter, 27% dark matter, 68% dark energy. It's almost miraculous when you think about it. Light that's been traveling for nearly 14 billion years carries within it enough information to tell us what the universe is made of. Not just what we can see, but what we can't see. The invisible majority, the hidden forces shaping everything. And here's a thought that sometimes catches me by surprise. Dark matter and dark energy weren't discovered by particle physicists in laboratories. They were discovered by astronomers looking at light, looking at galaxies, Looking at the CMB. By studying the universe on the largest scales, we found clues about the smallest, most fundamental components of reality. The cosmos and the quantum are connected, and light is the messenger between them. There's also a lesson here about how science works, about how our understanding evolves. For centuries, we thought the universe was made of matter and energy we could see. Then we found evidence for dark matter, then dark energy. Each discovery forced us to revise our picture of the cosmos, to admit that we didn't know as much as we thought we did. And that's okay. That's how knowledge grows, by being willing to change, to update, to follow the evidence wherever it leads, even if it leads to places that seem strange or uncomfortable. The universe doesn't care if its truths fit neatly into our expectations. It just is. And our job as curious beings is to observe, to measure, to listen, and to accept what the data tells us, even when it tells us that most of reality is invisible. So, when you look at the night sky, when you see stars and planets and the faint band of the Milky Way, remember that you're only seeing a fraction of what's there. The visible universe is like the tip of an iceberg. Most of the mass is hidden below the surface. Dark matter threads through galaxies like an invisible scaffolding. Dark energy fills the voids, pushing space apart. And the light from the CMB stretched and redshifted, and ancient carries the story of it all. But there's more, because the ripples in the CMB don't just tell us what the universe is made of. They also tell us about what we can't see, about limits, boundaries, horizons beyond which light will never reach us. And as we explore the edges of the observable universe, we're going to encounter one of the most profound ideas in cosmology. The idea that some light, some stories are written in places we'll never be able to read. There are places in the universe we will never see, not because they're too far away or too faint, but because the light from those places will never reach us. Not in a billion years, not in a trillion, never. There's a boundary out there invisible, but absolute, beyond which the universe becomes unknowable. A horizon not of distance, but of possibility. And that horizon exists because of something we've been talking about all along. The expansion of space, the stretching that never stops, the growing gap between here and there that eventually becomes too wide for even light to cross. Tonight, we're going to explore the edges of what we can see, the limits of the observable universe, the boundary between the knowable and the forever hidden. And we're going to discover that the cosmos, vast as it is even larger than we can ever hope to witness. Some stories are written in light we'll never read. Some chapters of the universe's history are closed to us, not lost, just unreachable. Let's start with a question that seems simple but isn't. How big is the observable universe? You might think the answer is straightforward. The universe is about 13.8 billion years old. Light travels at a fixed speed, so the farthest we can see is 13.8 billion light years in any direction. The observable universe should be a sphere with a radius of 13.8 billion light years centered on Earth. Right, wrong. And this is one of the most common misconceptions in cosmology. The observable universe is much larger than that. About 46 billion light years in radius, 93 billion light years across. How is that possible? How can we see things that are farther away than light could have traveled in the age of the universe? The answer, as always, is expansion. While light has been traveling toward us, the space it's been traveling through has been growing. So the objects that emitted that light have moved farther away, even as their light continues to reach us. It's like sending a letter across an ocean that's getting wider. The letter still arrives, but by the time it does, the sender is much farther away than they were when they mailed it. Let me give you a concrete example. The cosmic microwave background. The light we detect as the CMB was emitted when the universe was 380,000 years old. At that time, the region of space that emitted the light we're seeing now was only about 40 million light years away from where we are now. That's not very far in cosmic terms, but that light has been traveling for 13.8 billion years, and during all that time, space has been expanding. The region that emitted the light has been moving away from us, carried along by the expansion. And today that region is about 46 billion light years away. The light has finally caught up. It's reaching us now. But the place it came from is vastly more distant than it was when the journey began. So, the observable universe isn't defined by how far light can travel in a straight line. It's defined by how far away the most distant sources are now accounting for all the expansion that's happened since their light was emitted. And that distance is about 46 billion light years. That's the radius of the observable universe, the edge of what we can in principle see. But here's the thing. That's not the edge of the universe. It's just the edge of the part we can observe. The universe beyond that boundary still exists. It's still out there. We just can't see it. And we never will. Because the light from those regions hasn't had time to reach us yet. And depending on how fast the universe is expanding, some of that light might never reach us. This brings us to the concept of horizons. In cosmology, there are actually several different kinds of horizons. They all represent boundaries beyond which certain things become impossible, and they're all related to the expansion of space and the finite speed of light. The first kind is called the particle horizon. This is the boundary I've been describing, the edge of the region from which light has had time to reach us since the Big Bang. Everything within the particle horizon is in principle observable. Everything beyond it is not. The particle horizon is about 46 billion light years away in all directions, and it's growing. Every second, a little more of the universe becomes visible to us as light from farther regions finally arrives. The particle horizon is expanding at the speed of light, or rather at the rate that new light from distant regions enters our observable sphere. But there's another kind of horizon, a more troubling one. It's called the event horizon. And unlike the particle horizon, which grows over time, the event horizon represents a permanent boundary, a limit that will never be crossed. Light from beyond the event horizon will never reach us. Not now. Not ever. No matter how long we wait. Why? Because of dark energy. Remember, dark energy is causing the expansion of the universe to accelerate. Galaxies are moving away from us faster and faster. And at some distance, they are receding so quickly that light leaving them now will never catch up to us. The space between us and them is growing faster than light can cross it. So even though the light is traveling toward us at the speed of light, it's fighting a losing battle against the expansion of space. It's like running on a treadmill that's speeding up faster than you can run. You'll never reach the end. You'll just keep running in place or even fall backward despite your best efforts. The event horizon is estimated to be about 16 billion light years away. That's closer than the particle horizon, much closer. And here's what it means. Galaxies beyond the event horizon are lost to us forever. We can see some of them now because light they emitted in the past has already reached us. But any light they emit from this moment forward will never arrive. We're watching them in the past, and as time goes on, we'll see them freeze. Redshift into invisibility, fade from view, not because they stopped existing, but because the space between us and them is growing too fast for their light to ever bridge the gap. Think about what that means. There are galaxies out there right now that we can see, but we're seeing them as they were billions of years ago, and we'll never see what they look like now. We'll never know what happened to them, whether they merge with other galaxies, whether they form new stars, whether planets formed around those stars, whether life emerged. All of that is hidden from us. Not by distance alone, but by the accelerating expansion driven by dark energy. And it gets more haunting. As time goes on, as the universe continues to expand and the acceleration continues, more and more galaxies will cross the event horizon. They'll slip beyond the boundary. Their light will stop reaching us. And future astronomers, trillions of years from now, will see a much lonelier universe. A universe with fewer galaxies, fewer stars, less light. They'll look out into the cosmos and see mostly darkness. And if they don't have records from our time, if they don't have knowledge passed down through the ages, they might not even know that other galaxies ever existed. They might think the universe is just their galaxy, alone in an infinite void. That's a sobering thought. We live at a time when the universe is still relatively visible, when we can still see the distant galaxies, the CMB, the evidence of the Big Bang. But that window is closing, slowly, imperceptibly, but inevitably. Now let's talk about a common misunderstanding. A lot of people hear about the expanding universe and think it means everything is moving away from everything else, that galaxies are flying apart like shrapnel from an explosion. But that's not quite right. Expansion doesn't affect things that are bound together by forces stronger than the expansion itself. Gravity, for instance, holds galaxies together. The Milky Way isn't expanding. The solar system isn't expanding. You're not expanding. The atoms in your body aren't growing farther apart. Expansion only happens on scales where gravity and other forces are too weak to resist it. On the scale of galaxy clusters and larger. On those scales, space is growing, but on smaller scales, structure holds together. So, when we talk about the event horizon, we're talking about the distance at which the expansion of space becomes so dominant that not even light can overcome it. It's a distance where the recession velocity, the speed at which distant objects are moving away due to expansion, exceeds the speed of light. And yes, that's possible. Objects can recede faster than light, not because they're moving through space faster than light, but because the space between them and us is growing. Relativity doesn't forbid that. It only forbids objects from moving through space faster than light. The expansion of space itself isn't bound by that limit. Here's an analogy. Imagine two ants on a balloon. The ants are walking toward each other at a steady pace. But while they're walking, someone is inflating the balloon. The surface of the balloon is expanding, carrying the ants apart. If the balloon inflates slowly, the ants will eventually meet. But if it inflates fast enough, the ants will never reach each other. The distance between them will grow faster than they can walk. That's what's happening with light and the event horizon. The light is moving toward us, but space is expanding faster than the light can cross it. And here's where it gets really interesting. The event horizon isn't fixed. It depends on the rate of expansion. And the rate of expansion depends on dark energy. If dark energy remains constant, if it's truly a cosmological constant, then the event horizon will stay roughly where it is, about 16 billion light years away. But if dark energy changes over time, if it gets stronger or weaker, the event horizon could move. It could grow, bringing more of the universe within reach. Or it could shrink, cutting us off from even more. We don't know what dark energy will do. We barely know what it is. So, the future of the event horizon is uncertain. But what we do know is that there's a limit, a boundary, a horizon beyond which we cannot see. And that horizon exists not because of technology or distance, but because of the fundamental nature of space and time. There's something almost philosophical about this. The universe is teaching us humility. It's showing us that there are limits to knowledge, not limits imposed by our intelligence or our tools, but limits imposed by reality itself. Some things are unknowable, not because they're too complex or too subtle, but because they're beyond the boundary of the observable, beyond the reach of light, beyond the horizon. And yet, we keep looking. We keep building telescopes, launching satellites, mapping the CMB, measuring the expansion, searching for clues about what lies beyond. Because even though we can't see everything, we can see some things. And those things are worth seeing, worth studying, worth understanding. The observable universe is a gift, a sphere of light and information surrounding us. And even though it's just a fraction of the whole, it's enough. Enough to tell us about the Big Bang, about dark matter and dark energy, about the shape of space and the fate of the cosmos. Enough to show us that we're part of something vast and ancient and ongoing. But it's also a reminder that there's more galaxies, more stars, more stories, more light. All of it beyond the horizon, forever unreachable, forever unknown. Do you ever think about the things you'll never see, the places you'll never go, the questions you'll never have answered? The cosmic horizon is like that, but on the largest possible scale. It's a boundary between the knowable and the unknowable, and it's absolute. No matter how advanced our technology becomes, no matter how clever our theories, we'll never see beyond it. Some parts of the universe are simply not for us. And there's a strange beauty in that. A kind of peace. We don't have to know everything. We can't know everything. And that's okay. What we can know is enough. The light that reaches us, the stories it tells, the patterns it carries, those are enough to fill a lifetime. Many lifetimes. All of human history, in fact. We're still learning from the light that's already here, from the CMB, from distant galaxies, from stars that died billions of years ago. The universe is generous with what it shows us, even if it can't show us everything. So, as we move toward the end of this journey, as we prepare to close this story about the oldest light in the universe, let's hold on to that feeling, the feeling of standing at the edge, looking out into the vastness, knowing there's more beyond what we can see, but grateful for what we can. The horizon isn't a wall, it's a reminder that the universe is larger than us, older than us, stranger than us, and that our place in it, small as it may be, is part of a story still being written, still unfolding, still reaching us photon by photon from the edges of time. We've traveled far tonight, across 13.8 billion years, through plasma and transparency, through expanding space and stretching light. We've followed photons born when the universe was young, freed at the moment of recombination, journeying through dark ages and stellar births, across distances that keep growing even as they're crossed. And now, here we are, at the end of this story, or perhaps at the beginning of understanding. Because the oldest light in the universe isn't just history, it's present, it's happening. Right now, as you listen to these words, photons from the cosmic microwave background are falling onto Earth, passing through the atmosphere, through walls and trees and clouds, through you. Ancient light still traveling, still arriving, still telling its story to anyone willing to listen. And what a story it is. Think about everything we've learned tonight. We started with a simple observation. There's light all around us that we can't see with our eyes. Light that's been stretched into microwaves by the expansion of space. Light that was emitted when the universe was just 380,000 years old. A warm glow that has cooled into a whisper. The afterglow of creation itself. We learned that this light was once trapped, born into a universe so hot and dense that photons couldn't travel more than a microscopic distance before colliding with free electrons. For hundreds of thousands of years, light existed but couldn't escape. It was imprisoned in a fog of plasma scattered endlessly going nowhere. And then the universe cooled. Electrons paired with protons, atoms formed, and suddenly gloriously light was set free. It could travel. It could carry information across distances. It could become what we think of as light, something that moves through space connecting one place to another. That moment of freedom, that instant when the universe became transparent, is what we see in the CMB. Not the Big Bang itself, but the first moment afterward that left a visible record. The oldest light we can detect, the farthest back in time we can see. Everything before that is hidden behind the wall of opacity. But from that moment forward, we have light. We have evidence. We have the universe's own testimony. And that light has been traveling ever since. Not in a straight line across a static cosmos, but through an expanding universe, through space that's been growing the whole time. The photons have been racing at the speed of light, the fastest speed possible, and yet, the journey has taken nearly the entire age of the universe, because the destination kept moving away, because space itself was stretching beneath them. It's a race that light can't win, but also can't lose. It just keeps going. Patient, relentless, eternal. We learn that this ancient light has changed. What started as visible light, warm oranges and reds, has been pulled by expansion into microwaves. The wavelengths have stretched by a factor of about 1,100. The temperature has dropped from 3,000 degrees Kelvin to just 2.7 degrees above absolute zero. The light hasn't lost its information. It hasn't faded into nothing. It's just transformed, red-shifted, become invisible to our eyes but still detectable with the right instruments. And those instruments, COBE, WMAP, Planck, have given us something extraordinary. Maps of the infant universe. Pictures of what the cosmos looked like at 380,000 years old. Not smooth and featureless as you might expect, but modeled with tiny variations, hot spots and cool spots, temperature differences of only a few hundred millionths of a degree. Those variations are the seeds, the beginnings of structure, the places where hundreds of millions of years later, gravity would pull matter together into galaxies, into stars, into planets, into us. The patterns in the CMB tell us so much. They tell us the universe is flat, geometrically balanced, neither curving inward nor outward, but extending infinitely in all directions like an endless sheet. They tell us the universe is composed mostly of things we can't see. 5% normal matter, 27% dark matter, 68% dark energy. The visible cosmos is just the tip of the iceberg. Most of reality is invisible, hidden, made of substances we're only beginning to understand. And they tell us there are limits, horizons beyond which we cannot see. Not because of technology or distance, but because of the nature of space and time themselves. Light from beyond the event horizon will never reach us, no matter how long we wait. Some parts of the universe are forever unknowable. Some stories are written in places we'll never be able to read. But here's what moves me most. Here's what I want you to carry with you as we close this journey. The oldest light in the universe is still reaching us. Every night, every moment. It's been doing this for longer than stars have existed, longer than galaxies have lived in their current forms. And it will keep doing it, long after we're gone. Long after our sun burns out and Earth becomes a cold, dark rock drifting through space, that light will still be traveling, still arriving, still carrying its message about the universe's first transparent moment. There's something almost tender about that, something faithful. The light doesn't ask for acknowledgement, it doesn't demand attention. It just arrives, constant, quiet, patient, like an old friend who visits every day whether you notice or not. And we do notice. We've built satellites to detect it, instruments to measure it, careers to study it. We've spent decades, generations trying to understand what this ancient light can tell us. And it's told us so much, more than we ever imagined when Penzias and Wilson first stumbled upon that persistent hiss in their radio antenna back in 1964. More than Einstein or Hubble or any of the great cosmologists of the 20th century could have predicted. The CMB is a gift, a cosmic gift, a snapshot of the universe's infancy that we get to witness. And every time we look at it, every time we analyze its patterns or measure its temperature or study its polarization, we're reading a message from the past, from a time when the universe was simple, hot, dense, filled with potential, before stars, before galaxies, before complexity and structure and life, just hydrogen and helium and light learning to exist in a space that was finally transparent. Have you ever thought about how lucky we are to live at a time when we can see the CMB, when it's still detectable, still visible with our instruments? In the far future, trillions of years from now, the expansion of the universe will have carried so many galaxies beyond the horizon that future astronomers might not even know the Big Bang happened. They might not have access to the evidence we have. They might look out at a lonely cosmos, just their galaxy surrounded by darkness, and think that's all there is. That's all there ever was. But we live now, in this moment, when the universe is still relatively young, still relatively observable. We can see distant galaxies, we can detect the CMB, we can measure the expansion, we can read the story written in light, and that's a privilege, a profound privilege. So, what do we do with this knowledge? What does it mean to know that the oldest light in the universe is still reaching us? I think it means we're part of something larger, something older, something that began long before we existed and will continue long after we're gone. It means we're not separate from the cosmos. We're embedded in it, made from it. The atoms in our bodies were forged in stars that lived and died billions of years ago. The light falling on us now was born when the universe was still learning how to be transparent. We're part of this story, this ancient ongoing cosmic story. And that's worth remembering. It also means there's always more to discover, always more to learn. The CMB has taught us so much, but there are still mysteries. What is dark matter? What is dark energy? Why does the universe have the geometry it does? What happened in the first moments after the Big Bang, before recombination, when everything was too hot and dense for us to see? These are open questions, invitations to keep searching, keep wondering, keep looking at the light and asking what else it might tell us. And maybe that's the real lesson here. Not just the facts we've learned, but the process, the way we learn, by observing, by measuring, by building instruments and launching them into space, by staring at invisible light until it reveals its secrets, by being curious, patient, persistent. The universe doesn't give up its truths easily, but if you're willing to look carefully, to listen closely, it will speak. It will show you things you never imagined, things that change how you see reality itself. So, tonight as you drift towards sleep, as you let these ideas settle in your mind, I want you to remember something. The oldest light in the universe is falling on you right now. You can't see it, you can't feel it, but it's there. Photons that have been traveling for 13.8 billion years, carrying memories of a time when the cosmos was young and wild and glowing. They're passing through you, through your walls, through the air, and they'll keep coming. Tomorrow, the next day, forever. The universe's first light still reaching us, still reminding us that we are part of something vast and ancient and beautiful. And isn't that extraordinary that we, small and brief as we are, get to witness this, get to understand it, get to stand at the edge of time and look back toward the beginning? That's not just science, that's poetry, that's connection, that's the cosmos recognizing itself through us. So, thank you. Thank you for joining me on this journey, for drifting quietly through the science of light and time and expansion, for letting curiosity guide you through ideas that might have seemed strange or difficult at first, but became something else, something beautiful, something worth knowing. I hope you found comfort in these quiet hours. I hope you found wonder. And I hope when you look up at the night sky from now on, you'll think about the invisible light all around you, the ancient glow, the universe still whispering its first words. There are more stories waiting, more journeys through the cosmos, more quiet nights where science meets wonder, and we drift together through the mysteries of existence. If you'd like to join me again, I'll be here, ready to wander, ready to whisper, ready to explore the universe one gentle story at a time. Until then, sleep well, dream gently, and remember, the oldest light is still traveling, still reaching us, still here. Good night.